Okay, let's look at equilibrium. So equilibrium steps do crop up time to time in more chemical systems, but where do they really show up a lot? For those in more biological classes. Have you guys had to memorize the Krebs cycle, glycolysis, all of that crap? Yep, I hated that. I hated the memorization, but I had to do it. Did you notice how many equilibrium steps are in, I don't remember now, the Krebs cycle? Yeah. There's a reason for that, so things don't get converted right away and you just get energy or whatever. I actually don't know what the Krebs is. The Krebs cycle the one that is about ATP, or is the Krebs cycle something else? Okay. Yeah, that's all I remember. ATP makes the energy. Okay. There's a reason for that, so that way everything doesn't get converted right to energy and you just die, or else we'd have to be just constantly consuming. However, if we wanted to study like metabolism generally has a ton of equilibrium steps. So biological systems have lots of equilibrium steps. So if you wanted to study the rate, which is incredibly important for toxicology studies, drug analysis, and so on, you have to know these sort of things to get through that point. And a lot of times, if you're going through the FDA or other aspects, you have to try and prove some sort of rate mechanism to show those individual steps, or to better understand, hey, I need to target this step to make some biological response I want to happen or not happen to occur. So let's talk about reactions approaching equilibrium. My one friend, he works for Regeneron. He deals with this data all the time. I feel bad for him. He was like a kinetics person. I am extremely thankful those people exist, but I would not want to be one of those people. Oh, I guess I should spell out equilibrium. What is the definition of chemical equilibrium? Right. Rate of forward reaction is equal to the rate of reverse reaction. Do the concentrations of the products and reactants have to be the same? No. Okay, we're going to consider the following reaction. We're going to have A at equilibrium with B. We have an constant associated with the forward reaction. That's a little k, not a big K. We're going to use big K in a minute. I'll use a different color to specify that. And then we'll call the reverse K minus 1. We could look at A or we could look at B in this case to determine the rate. Let's investigate it with A. So consider the change in A over time. So we have to look at spots where A is being consumed and produced. In which reaction is K being either consumed or produced? Yep, so we're going to have the reverse reaction. If we wanted to write a rate law for the reverse reaction, what would it be? Yep. Yes. That's where it's being produced, right? What about consumed? Yep. we'd have k sub 1, and we would need a negative sign associated with it, showing that we're taking some of it away. K sub 1 times what? Yeah. The negative sign indicates that it is being consumed. Because we're talking about the change in A over time. Notice we are not saying this is equal to the rate right now. We're just looking at what happens to A over time. Does that make sense? Yeah. All right. What we're going to do is we're going to set up some reaction conditions where we only start with A. We're going to see what happens. No B. We're just talking about initial. Concentrations, we're going to start with a concentration of A naught. And notice, what's the stoichiometric coefficient between these two? 1. So if we look at the concentration of A and B at some other time, how does that relate to A naught? Given that they're in a 1-to-1 stoichiometric ratio. Yep. The concentration of A plus the concentration of B at some other time, right? Okay. What we're going to do, let's reorganize this so we can get rid of the term B. How would you reorganize this so we had a B is equal to what? Yep, A naught minus A. Should give us the concentration of B. Again, because they're in a 1-to-1 stoichiometric ratio. So now, let's take this expression. We're going to plug it in here. So we get dA dt negative k sub 1 A. And what happens with that B again? Yeah. Okay, we can simplify this further. What terms could we lump together? Yeah, we're going to slap the A stuff together, and we're going to leave the A naught stuff alone. So we get negative k sub 1 plus k minus 1 A plus k minus 1 A naught. Okay, to erase this bit up here. Okay. What we're going to do next is we're going to rearrange this equation to have A terms by themselves and T terms like isolated. Rearrange. Basically, we're going to have dt by itself. We'll have dA over here. What are we going to have on this side then? One over what? So we move that one over to that side, right? Just focus on this thing right now. What are we going to do to all this junk? Yep, go slap it all over there. K1 plus K minus 1 times A Okay. Anybody want to do this integral badly? So we're going to do an integration. Both sides, 0 to t. What are we going to do here? Let's start at a naught, and what are we going to go to? Yeah. A at some other time. I'm going to leave off the sub t, though. Anybody care if I just run to the end with that one? You should not. Okay? If you do, what I will do is give you a table of integrals, and you just plug things in. You define an A, you define a B, go with it. Okay. We're going to rearrange some things around to make our lives a little bit easier. But you integrate this thing, and what you should get in the end. Okay. Once we get that scrambled down. This looks ugly. Is there any way we can get rid of some stuff? Because we want to isolate A by itself. Concentration of A. We are going to exponentiate. I would wait for a little bit for that one. Yeah. This thing, since there's a positive here, -1 can go away. And then, LM, we are going to exponentiate. After we do that, we get negative k sub 1 minus k negative 1 A plus k minus 1 A naught Okay. Let's try to simplify a bit further. Yeah, is that what you're going to say? Yeah, this k sub -1, we could split these up into two different fractions. And what you would end up getting, these A naughts are going to cancel. And you get k let's write this out. A negative sign is going to cancel out too. Yes. Mm-hmm. Yes, right here. Yeah, that's a -1. Sorry. Okay, we're almost there. We want to isolate this thing by itself. If we do a little more manipulation, just some algebra, I feel like people can get to that point. What you're going to arrive at is this expression, which was on your daily problem. Yeah. Sorry. Shouldn't have been a negative there. So you can flop this thing around and you get to this. At any time that you want to measure A, that's the expression. How many people like that? No, that sucks. That's ugly. We have to know all these K's. We got to throw in an E term. What the F? We can know we've... Anytime. However, what type of reaction were we considering here? No, actually, no, that was last time. We were looking at an equilibrium, right, of A going to that. What about at equilibrium? So question I'm going to ask. How experimentally can you ensure you are at equilibrium? Yeah. Let it go for a really long time. Leave it alone. Don't probe it. Don't mess with it. Just leave it. In a perfect world, if you wanted to measure equilibrium, how long would you wait? Forever. So what would time go to? Yeah. Of course, we can't ever do that because we'd like to study a chemical reaction within our lifetime. Let's consider the equilibrium expression for what we have. What's the equilibrium expression equal to? It's always what over what? Yep. We're going to keep track of B at equilibrium and A at equilibrium. So now, let's first look at A at equilibrium. We have this expression here. T out of there. And what do we say about time at equilibrium? How does that benefit us with our expression? Yeah, this thing. We got E negative k of 1 minus k minus 1 times t. T is getting really big, right? This whole exponent up here, you're being multiplied by negative constants. This means it's e to a really big negative number. What does that approach? Yeah. So what could we approximate this to be then? What happens to this term? Yeah, it's 0. So how could we rewrite this? So what happens to this part? Just 0. So what do we get? Mm-hmm. Times, yeah. That is much easier to work with. Okay, we have A dealt with in this expression. B, let's explore B. How did we initially define B? The concentration of B at some time? Yeah, that guy, right? So if we wanted B at equilibrium, what do we got to subtract off? Yeah, A at equilibrium. This just becomes A naught. We plug in our expression here. Okay. We can simplify that a bit further. How would you simplify this thing? I'm sorry, yeah, pull out the A naught so you get 1 minus. And then if you want to simplify this further, you can multiply by a common factor, slap everything together, and what you should get in the end is that guy. Okay, now we have an expression for A and B. Let's plug in and see what we get. B at equilibrium, A at equilibrium, plug in our expressions. Dang. Can we simplify this? The A naughts are the same, right? So they go away. Anything else? Yeah, those are gone. And what do we end up with? Awesome. Why is this cool? You might be asking that about the entire class. What type of properties are these? Kinetic, right? What type of property is this? Thermodynamic. We've connected a thermodynamic property to a kinetic property. There's a lot of power there. Just got connected. So the kinetics, they're connected to thermodynamics too. Everything is thermo when you really look at it. Unless you look at quantum particles. And that's what all next semester is about. Anybody who would like to sit in on it, go right ahead. Those that are forced to be in that class, I'll see you next semester to talk about that. Are there any questions about this? We really didn't have enough time to talk about mechanisms. So I'm going to try to make a video about mechanisms also. Okay? Any questions at all right now? What would you be expected to do on a Quizlet might be one. Keeping in mind when we're talking about equilibrium, waiting at really long times, what happens to that expression? And that's basically what your daily problem's about, right? Any other questions, comments, or concerns?